Start recording. Okay. So let me show you a video of the flow over. I cannot minimize. You cannot minimize Zoom when you are recording the meeting. So how do I play it? Okay.
You could post the link and then send it to us.
Okay, it's a file. Okay, it's not the video, but let me open it up through here. That is a video of flow over a cylinder. Okay, and okay, here we go. Find it. Let me start it first, and let's see if I can share it. Okay, now let me share the screen. Okay, do you see it? I don't know if you see it. It's anybody?
Yeah, we can see it.
Okay. So what does this video look like? Okay, there's a cylinder in there. There's some color inside the cylinder, but don't worry about it. This is not supposed to be color. It's just a solid cylinder. Okay, the color representing the outside of the flow color representing the vorticity. Okay, so the flow is from left to the right. The cylinder moves a little bit, oscillates a little bit, but if it's not oscillating, that's same flow patterns. Okay, so you will see the vortex, one on the top, one on the bottom. It generates. This is for the low Reynolds number flow. Low Reynolds number about 200 here. I think also in the textbook it has some pictures. Page 298, figure 6.13, also shows some detailed flow structures of flow over a cylinder. But that's the flow. What the flow look like? The color, the vorticity is a vector, so it has positive and negative. The red is positive, blue is negative, but they have the same strengths. Okay, it's just a direction. So one on the top of the cylinder, one on the bottom cylinder, gradually. This is called vortex shedding. Okay, so that's the flow phenomenon. Okay, then, so what about the heat transfer? What does the heat transfer look like in educated gas? So the flow have created vortex going downstream. Okay, so with the movement of the vortices, the heat being carried away basically exactly follows the trajectory of those vortices. Okay. Let me play another video about the heat transfer for the same case. Okay, I have another video for heat transfer, heat. Okay. Okay, open with. They use a little different color scheme. Now it's a color representing the temperature. Okay, for that same case, now you will see, let me share that screen again. Can you see that video? Anybody, can you see it?
Yes, sir.
Okay,
Yes, sir.
Okay, good. Now the color representing temperature, I think it's an isothermal temperature condition. So on the cylinder surface, it's heated with a high temperature. Red is high temperature. The background blue is low temperature, ambient temperature. So you see the heat is transferred through the surface. Actually, mostly the heat transfer in the wake behind the cylinder. Again, flow is from the left to the right. Okay, so you will see that's exactly identical to the flow pattern. Okay, so the flow, basically what I tried to convey, the convection heat transfer for flow over a cylinder is basically dictated by the flow pattern, by the vortex shedding. Your vortex going out like this, you carry the heat out too. Okay, so a little bit high temperature being moved to the surrounding. Okay, behind the cylinder. Okay, so this is the mechanism of convection heat transfer of a flow over a circular cylinder or a sphere will be similar to, okay? So the question is here, okay, so it seems like it's a very, very complicated phenomenon, okay? So you have to solve the flow field before you can actually calculate the Nusselt number, right? Nusselt number, Reynolds number, those things. Nusselt number is the heat transfer, okay? So, okay, let me turn it off. Let me turn my whiteboard. So again, for this problem, we use a lot of empirical solutions to decide the heat transfer coefficient, Nusselt number. And before we talk about Nusselt number, always we need to talk about the drag, right? Surface resistance or drag. In this case, it's not only surface resistance, it's the total drag, okay? So you flow over an object like this, it will, produce drag. Drag is sometimes it's good. It's bad, right? You have to overcome the drag to hold it.
You're saying.
Yes.
So like, is this like kind of like a pipe, or like what's a real world object that it would be like?
This is pipe. Yeah, it should be. It could be a pipe cylinder. This is the 2D view. It's a cross section.
Okay.
Cross-section view of a cylinder.
So what's the difference? You were saying there was a difference between this and what we did before. So like, what would be like the real world like object difference? Like, is it like a different pipe?
Before is a pipe, yeah, pipe flow inside the internal flow of the pipe. This is the external flow.
Oh, okay, I got
you. Okay, that's the flow over outside the flow. Okay, so
okay,
totally different. And the flow field is more complicated in the external flow. Inside the pipe, it doesn't have this complicated features. You have little turbulence maybe, but that's small scale. Here you see the vortex. It's a larger scale. Okay, vortex, and then your heat transfer is actually followed the vortex shedding. It's difficult to mathematically have a analytical solution for that flow field. So in that sense, you don't have an analytical solution for the heat transfer either. Okay.
So is this like something like when you're in the industry, they would like take these images to see like you only want so much temperature or something like coming off the pipe, so like you would like use this to like...
One of the application is a cross-flow heat exchanger. You want to remove heat of the pipe, okay? So one of the common practice is blow air to it, or put a liquid through it, or blow air to it to blow the heat away. This is the application, the cross-flow heat exchanger. So it's a cross-flow, blow to it, then it carries the heat away.
Okay, so just to cool down like whatever pipe.
That's cool down. Heat transfer, that's the application, right? Try to remove the heat, cool it down, okay? So again, this is even more complicated than the internal pipe flow, okay? External flow is, it's too complicated to have analytical solutions. So most of the Nusselt number, drag coefficient, those things is from empirical study or from experimental measurement, okay? So let's take a look of the first thing is the drag. Before we talk about the Nusselt number, heat transfer coefficient, right? We always wanna talk about the drag, okay? So let me turn on a whiteboard. Yeah, if you have any question, please jump in. Let's discuss it here and make sure everybody understand. Okay, do you see my whiteboard?
Yes, sir.
Okay, the first is drag. Why drag is important? You need to hold it, right? If you don't hold that pipe, it will be blown away, basically. Okay, that's the drag. Okay, so we created something called drag coefficient. So the drag force, okay, in the external flow, drag force, it's not only a cylinder or sphere. Maybe you design a race car or whatever, that also has drag force. It's one of the most important thing to consider, right? Drag force is always calculated by CD. You may look at, you may saw the coefficient CD before. It's called drag coefficient. The equation is equation 6.16 on the textbook. So Okay.
I'm sorry. What equation was that in the textbook again? I'm trying to follow along both of y'all.
Equation 616 on page 294. Okay, that's half rho u square times the A is the frontal area times a drag coefficient. This is the drag force. In the race car industry, also the same equation to calculate the drag force. Or in the airplane design, you need to calculate the drag, same thing, okay? So that's the equation. So drag coefficient is one thing what people look at to see if the drag is big or small, okay? So the drag coefficient, it's a dimensionless coefficient. If you times half rho u square times the frontal area, then it becomes the drag force. Okay, so let me send you two figures in the textbooks, 6.9 and the 6.10. I text you in the group me. I have the picture copied here. This is 6.9 first. This is for the cylinder. Okay, the second one, oh no, I'm sorry. The first one is for the sphere. Okay, the second one is for the cylinder. That's a very, very important plot you want to look at. Okay, see, so from now on, everything is, you know, in this heat transfer topic, it's not difficult. So you look at the coefficient, so you find out the coefficient, then you can just basically easily calculate the equations. For example, here is for the drag force. So the drag coefficient, let's look at the second one. Second one is the cylinder, right? The vertical axis is the CD, is the drag coefficient. The bottom horizontal axis is the Reynolds number. Okay, so
It
based
hasn't
on
sent yet.
what you say?
It hasn't sent.
Okay, so wait a little bit. Oh no, I'm sorry, I sent it to the wrong one. Okay. Hold on, I sent it to the wrong class. The other class probably be curious why I sent this. Okay, let me find our class.
Dr. Zhang, quick question.
Yeah.
On the drag force equation in the book, in the denominator, that fraction, it has 2 times GC, and I was just wondering why you didn't put it in
That's
your.
That's a correction. That's a difference in the gravitational acceleration. I don't think you need that. Just half rho u square. Okay. Let me find our class. I must.
How come we don't need that? Like, what's the reasoning for that?
Okay,
I'm
let's
just
see.
curious.
What is the GC? What did the textbook said about GC? I think that's a wrong equation. It's a typo. You shouldn't, because now you use half rho u square. It shouldn't have g down there. Let me see. What does it say about the GC? I'll find out later, but you don't need the GC. This is the correct equation, half rho u squared. That's it. That's all you need to use to calculate the drag force. Okay. Now this is two tables, two plots. I want to send you 610 and 6.9. This is for the drag coefficient for the cylinder and for the sphere. Sphere is 610. Okay. Cylinder is 6.9. So take a look of these two plots, and the vertical axis is CD, is the drag coefficient. Okay, the bottom axis here is the Reynolds number. So you need to know the Reynolds number in order to calculate to find the drag coefficient from the table, right? So what is the Reynolds number? Anybody remember? So I had a question from a student before. Said, hey, why you use this viscosity mu, or sometimes you use the other viscosity? They are the same thing, because dynamic viscosity is kinematic viscosity is dynamic viscosity divided by rho. So it depends on the table which viscosity you get. So that's the same Reynolds number calculated from. Okay, be careful, but in most of the table, it shows dynamic viscosity as well as the kinematic viscosity. But some table may be just showing you the kinematic viscosity. But if you use that viscosity, there's no row on the numerator for the Reynolds number. Okay, so D is the diameter of the cylinder or the sphere. Okay, so you calculate the Reynolds number, then from this plot, it shows you should be able to find your drag coefficient for your case. Okay, then you can calculate the drag force based on this equation here. CD times half rho U squared times the frontal area. A, be careful, A is so-called frontal area. What do you mean by frontal area? So what is the frontal area of a cylinder? So then for them flow over this
The
cylinder.
first half.
Well, how do you give me an equation? So let's say the diameter is D. How do you calculate the frontal area of the cylinder?
Pi r,
I'll give you a D. Can you use D?
half pi d.
Okay, let's say a cylinder.
Oh,
You're
times-
right. You're right. You're right. Definitely, you're right. If we talk about 2D, yeah, it is pi.
half
pi-
pi d times length.
Yeah, half pi d or half pi d, right? Then you times the. In reality, it's a cylinder, so you times.
Times the length of the cylinder or the height.
Cylinder, yeah. Okay. So, oh no, I think the frontal area is not like this. Frontal area is, I think it's, frontal area is what you actually, when you look from the front, it's not this. Frontal area. If you look from the front for the cylinder, okay, so this is the H, this is the D. Okay, so when you look from the front, what is the area looking at? Anybody? It's actually in this drag force industry, the frontal area is D times H.
So a rectangle.
That's a rectangle. That's when you look at it from the front, what's the area you see?
Okay. Okay. So I have a question. So
Yeah.
that's just diameter times just the length of like the whole pipe, or like are we like a certain section, or what do
Well,
we
certain
know?
section, it's a section of interest. What you're interested in? You, in a real practical application, you're interested in a pipe. Okay, when the flow go cross it, right?
Okay. So the
If
frontal
it's
area.
outside the flow, it doesn't matter to you, right?
Okay. So it'd be like a specified like length for the frontal area, like H would
Depending
be-
on you know the flow, right? Do you know the flow? You know the flow below to it, the portion that experience the flow. Otherwise, the other portion you don't have the flow on it, right? You don't have that force. Is that right? So that's the portion of the area of interest. If you don't have the velocity, of course you don't have the drag, right? Only the portion will be experienced by the flow. Experienced the flow, then you have the drag from the flow. Okay. So this is the drag. Okay. So that two. Did you see that two plot I sent it to you? Okay. One is for sphere. Okay. 610 is for the sphere. 69 is for the cylinder. Okay. So it looks the same, value are different. Okay. So let me ask you this: what is the frontal area of a sphere? Let's say the sphere has a diameter d. What is the frontal area of the sphere? Let's say your air blow to a sphere.
Is it the area of the circle?
That's right. It's quarter pi d squared. So for the sphere, okay? This is for the cylinder. Okay, so the equation is the same. Drag coefficient equation, okay? So, but area, be careful, depend on the sphere and the cylinder. Okay, I remember when I was in graduate school, one time in the advanced heat transfer or advanced fluid, I forget which class, the professor actually asked a question, you know, I play golf, you know, did you see golf balls? Why golf ball has dimples on it? By chance, anybody know here?
I've heard of that one where it
There's more lift and stuff.
Huh? What'd you say?
It has something to do with it causes more lift.
I think we're talking about drag here.
yeah.
Yeah.
It's actually related to the drag. Okay, look at that plot I gave you. Sphere was 6.10, right? 610 plot. Look at the CD at the end of the spectrum, Reynolds number spectrum. What do you see?
It drops.
There's a drop, sudden drop. Is drop good or bad?
Good.
Drop is good, right? Then the drag coefficient is smaller, drag force is smaller. You have reduced the drag. See, when the Reynolds number is high, okay, Reynolds number is high, then it starts to show drag. When the Reynolds number is high, you see Reynolds number in the external flow, like for the cylinder or sphere, like 100, maybe that's the laminar. Okay, maybe the critical Reynolds number is about 1,000. Okay, I think like below 100 is definitely laminar. Okay, greater than 1,000, we treat it as turbulent flow. Okay, flow over a sphere. Okay, for example.
Why
So
does it go back up at the very end?
what's at the very end?
The chart seems like it's going back up a little bit after the drop off.
Yeah, right now, okay, listen to me, I haven't finished yet. So basically the higher the Reynolds number is, the more turbulence you will see. Okay, so the critical Reynolds number is 1,000 for the external flow. Okay, so greater than 1,000 is turbulent flow, right? If bigger the Reynolds number, it's more turbulent. Okay, so now it seems like if you have a very turbulent flow, when the Reynolds number reaches to about 3 times 10 to the 5, okay, then it suddenly the drag reduces significantly. Okay, but when you play golf, okay, you know, 300 years ago, all the Scottish, when they play golf, the ball is actually indeed smooth, no dimple on it. Okay, it's just a circle, sphere, and no matter how hard you hit, okay, you're not gonna reach to that 3 by 10 to the 5 Reynolds number. Okay, even the strongest person probably go hit, maybe you can reach to that much Reynolds. You know, Reynolds number is coming from the speed, right? Look at this, diameter of the ball doesn't change. Viscosity of the air doesn't change. What you can control to increase the Reynolds number?
The diameter.
No, diameter doesn't change. For a golf ball, ball is there. You're playing golf ball. Okay, your goal is to increase the Reynolds number so that your drag will decrease. So how to increase the Reynolds number if you are the golfer?
Increase area?
No, look at the equation, Reynolds number.
The velocity.
Okay. Velocity, that's the only thing you can change. You hit it harder. Is that right? Everybody? Okay. I guess the strongest person on the earth probably still couldn't reach to that Reynolds number. Okay, you're hitting hard enough, but still, you couldn't reach that Reynolds number. You're never gonna see that drop. Okay, so, but hey, that doesn't matter. Here, increase Reynolds number is just to increase the turbulence. How about we modify the surface to increase the turbulence? Okay, so all Scottish actually find when the ball getting old, very rough, you know, non-smooth anymore, then suddenly it flies further. Okay, we find that. Okay, so that leads to some thoughts. Some scientists at that time, 200-300 years ago, they say, hey, what about, you know, we make it even more rough. You know, we put a dimple on the ball. Okay, dimple on the ball actually it creates the onset of turbulence a little bit earlier. it's easy to create turbulence. For example, you have a surface, you have some structure on it, not smooth, very rough. You know, it's very turbulent flow. So you create onset of turbulence early with a little bit lower Reynolds number. Maybe it's like a 1/10⁵. With that little bit surface roughness on the golf ball, you feel the same effect as a little bit higher Reynolds number. Okay, so suddenly you reach to that gap, that reach to that jump. Okay, so then the ball fly much further because the drag is smaller. Okay, so that's the reason why the golf ball had dimple. It make it fly further. Okay, so but still you probably need that strength to get to that threshold. Okay, to become a professional and the non-professional. That's the difference. You can reach to that. There's a science behind it. Okay, you're powerful enough to reach to that drop of the drag coefficient. Then you become pros. Okay, so that's about the drag coefficient. Okay, so see, sports science, right? A lot of sports actually, there's a science and physics behind. Okay, so this is the drag. Now let me present you some equation for the Nusselt number. Now we need to look at the heat transfer. Flow and heat transfer always a twin. They are very related, especially in the convection heat transfer. Okay, for flow over a cylinder, the first equation I want to give is equation 6.17. Okay, it's not that great, but still people using it. The equation is short. Okay, there's a coefficient. Okay, velocity times diameter divided by viscosity of the fluid, and I think this viscosity of the film. Okay, power of n, Prandtl number of the film temperature. Okay, 1/3. Okay, so here, the equation for the external flow, the isothermal and iso heat flux are almost identical. Okay, the effect of the heat transfer. Two type of boundary condition. Two type of boundary condition doesn't matter that much. Okay, let me share my screen. I show you actually a paper. Okay, let me turn on that paper. In that paper, one of the conclusion is actually the iso heat transfer or isothermal and iso heat flux condition are actually identical. No, hold on. Did I open that paper? Okay, here we go. Did you see that paper? International Journal on the Heat and the Fluid Flow. Okay. This is actually a chemical engineering journal. They talk about heat transfer a lot, convection heat transfer. Why I only see white and blank pages? Did you see anything? Okay, here we go. Okay. Actually, it's my paper. I'm the first author for this paper. Heat transfer over circular cylinder. I want to show you a actual result. We conclude that's one of our contribution is we put together iso heat flux and isothermal boundary condition of the heated cylinder. Well, most of the paper talk about the local Nusselt number. Okay, that's the one I want to show you. Figure 6. Did you see that figure 6 down there?
Yes, sir.
Okay, we plotted a little Reynolds number region from 20 to maybe maximum 200 Reynolds number. For the high Reynolds number, share the same pattern. You see, there the previous study about the isothermal condition with the same Reynolds number, iso heat flux condition. Okay, our simulation model for the iso heat flux and isothermal are almost identical also with all their studies. So Nusselt number increases. Okay, this is the overall Nusselt number we're talking about, where it's not local Nusselt number. So for example, a cylinder, what is the overall Nusselt number, heat transfer coefficient, right? It's average. So it increases with the Reynolds number, increase of Reynolds number. Okay, that makes sense, right? Because when Reynolds number increase, is the heat transfer increase or not? When Reynolds number increase for a same object, that means the velocity increases. Okay, if the velocity increases, your convection heat transfer is supposed to increase. Yeah, is that common sense? You have bigger flow, you have bigger heat transfer. Okay, convection. So Nusselt number is just heat transfer coefficient. Okay, so it will increase on that. Okay. So in that paper also we have a flow field, right? Temperature field. I think it's also reported here. Okay, see that's a temperature control of the flow over a oscillating cylinder 200. So you see the surface is heated, then the temperature, the heat is transferred in the downstream wake of the cylinder. Okay, so that one I want to try to convey that the.
So Dr. Zhang, you said for a second there was something about like for chemical engineering. How like what all did y'all do that like applies over to like the
chemical engineering? Chemical engineering do the heat change a lot. Cross flow heat, they're going to remove heat. They're going to control the process. So heat transfer is really a very important topic for chemical engineers.
Okay, I got you.
Yeah, yeah. It's a process. Process you have to control. The heat is one of the things you need to control. Let me go back to my whiteboard. So this equation, so most of the equation all works for the isothermal and iso heat flux condition. So that's a little bit easier for you. Okay, you don't have to decide what is the condition, what is the surface condition. Constant temperature or constant heat flux through the surface, it's fine. There will be the same equation. So because their result, the Nusselt number doesn't change between the two boundary conditions. Okay, there are two coefficients here, C and N. Okay, so there's a table on the textbook, table 6.2. I can take a picture, send it to you. Okay, so let's see. It tells you the C and the N for different Reynolds number. Okay, so these are the two coefficients for different Reynolds number. The Reynolds number range from 0.4. Okay, did you see that? Do you see the table I posted? Please follow me in my class. You see I give you a lot of quizzes like this. I just want to make sure everybody follow me. Okay, come with me. Okay, so you can save your time after school. I try to make sure you learn it during the class time. Okay, so Reynolds number, the range for this equation from 0.4 to 400,000, very big Reynolds number. So with different Reynolds number range, you will have a C value and N value. So you need to calculate the Reynolds number anyway, right? So to find the appropriate C and the N, so to use this equation 6.17. Okay. It's not the most accurate one, okay? So, but it can be used, okay? A little bit more accurate one will be 6.18. This is 6.17. These are all cylinders, okay? 6.18, right, like this. Nusselt number equals to 0.35 plus 0.56. Reynolds number 0.52, power of 0.52 times Prandtl number, power of 0.3. Okay, So this equation works for the Reynolds number in the range from 0.1 to 10 to the 5. A little bit less range, but the claim is a little bit more accurate, okay, for this Reynolds number range. A little bit less range than the previous equation, 6.17, okay. Again, these equations, they said Reynolds number F, Prandtl number F, which means those properties are evaluated from the fume temperature.
So is there a difference between 617 and 618? Because I see in the book it says Nessle's number is DF and then Nessel number F. Like, is there a difference between those? Or
it doesn't matter. I don't think there's a difference. That's basically all from the D. D basically means it's from the diameter, Nessel number, but it's just one object there. It's the diameter, so it's the same thing. So, but more importantly, you have to make sure that the property is evaluated from the fume temperature. Okay, fume temperature. Do you still remember what is the fume temperature?
It's the average of the wall temperature and the well, liquid temperature.
That's right. Fluid, not necessarily liquid, right? So it's a fume temperature. Okay. Some of the equation you will see later is estimated from the fluid temperature only. Okay. So the property is different. Be careful. The property, you know, with different temperature, some of the property changes significantly. Therefore, it will change your Nusselt number significantly if you use the wrong temperature to evaluate the property. Okay. So, but these equations are all from different groups, you know, from different researchers. They focus on a different range of Reynolds number, basically. Okay, so they claim in this the smaller Reynolds number range, it's more accurate than the previous equation. Okay, then there are too many equations. Okay, I give you another picture. Equation 19 and 20. These are the two equations also in from other researchers. They are from the same group. Let me take those pictures. I think it's difficult for me to write. Okay, so let me send it to you. 19 and 20, that's the same set of equation. Okay. These are the same equation, same set of equation, but it's for the different Reynolds number range. So they separate this, the whole Reynolds number range is from 1 to 2 to the 10 to the 5. But the first one, 19, is for the Reynolds number range from 1 to 1000. Okay, basically it's a less turbulent region. Okay, so equation 6.20 is from 1000 Reynolds number to 2 by 10 to the 5, which is a turbulent region. Okay, so this is the equation. Some group claim their equation is better than the other groups. Okay, so yeah, they claim their equation is very it's within some agreement with the equation like 6.17, but with different group, different Reynolds number range. Okay.
Dr. Zhang.
Yeah.
What is the Prandtl's number W that's in the denominator of that fraction? I assume F is for film.
Yeah. That's the Prandtl number evaluated by the wall temperature.
Okay.
Okay, F means fume temperature. So the numerator is the Prandtl number evaluated by the fume temperature. Notice there's another Prandtl number in these two equations. That's the Prandtl number, just Prandtl number without the F. Then that's the Prandtl number evaluated by the flow temperature. Okay, so you need to be really careful on applying these equations. Okay. That's a good question. So I want to write notes here for you to remember. So property will be estimated, will be obtained by 3 temperatures, okay? Especially, I think it's just the Prandtl number, okay, not the other properties. PR. So if you use these two equations, 19 and the 20, be careful. Water temperature, film temperature, and the fluids temperature, okay? The other equation I want to give, equation set, is 6.21 and the 6.22. Okay. The 21 is, I think, already in this picture. It's already there. And let me shoot the 22 for you. Okay. Okay, I actually, yeah. Okay, so the requirements, they're including a Pickett number, PE. Do you remember what is a Pickett number? Pickett number is Prandtl number times Reynolds number. Okay, so it gives you a little bit restriction on the heat transfer. Okay, on the Prandtl number. It's not only Reynolds number. Okay, but for the 6.621, that's the Reynolds number range from 100 to 10 to the 7. Okay, pretty wide range. And the 6.22 is a little bit narrower for the Reynolds number. It's 20,000 to 400,000. Okay, so for that, and both Pickett number, both equations, Pickett number should be greater than 0.2. Okay, Pickett number is Prandtl number times the Reynolds number. So you'll see most of the time is greater than 0.2, unless you are dealing with very, very small heat transfer in a small structure, small heat transfer surfaces. Okay, so these are the equations. And I think they use fluid temperature to evaluate this Nusselt number. I think I can answer one of your questions before you say, what is the Nusselt number F and NUF? That's the other is Nusselt number. No, the other is also Nusselt number F. Yeah, both of them. If it's Nusselt number F, basically it's that property is evaluated from the film temperature. Here, equation 6.21 and equation 6.22, be very careful. Their Nusselt number is evaluated by the property from the fluid temperature, not the film temperature. Okay, that's why the Nusselt number here is just Nusselt number, not Nusselt number F.
So what is it if it's Nusselt number DF? That was one of them. Is that the?
Yeah, I think this is a typo or whatever. I don't see any difference between Nusselt number D. Nusselt number, it's all from the D. Okay, so it's all from the diameter. Okay, so one cylinder or one sphere, that's the diameter. I don't see the difference. I don't think the book even mentioned that difference. There's an inconsistency on the writing in the textbook. Okay, some places. Okay, so these are the cylinder. There's also 6.23, 6.24. I don't think that's too many equations. Different Reynolds number range. So you can pick one. Okay. And the sphere also presents you so many equations on the heat transfer Nusselt number. I just want to use, usually we just use the last one, 6.30. It serves a good Reynolds number range and a good Prandtl number range. And from my knowledge, it's commonly accepted. It's have high accuracy. So for the sphere, how many time do I have? Okay, I have 2 minutes. So I'll give you an example next class. So Nusselt number for sphere, 6.30 is a good one to use. But if your Reynolds number and the Prandtl number out of that range, very unlikely you'll see a case out of that range, but then you can have the other equation to use on top of 6.30, okay? So I like to use that equation. So just give it to you, write it down. 0.4 Reynolds number to the half. Again, this equation is evaluated from the fluid temperature, the properties, okay, from the fluid temperature. You don't need the film temperature for apply this equation, which is simple, a little bit easier. I think that's why those researchers, they try to use the fluid temperature to evaluate the property, because film temperature required water temperature sometimes it's difficult to obtain if it's not a isothermal condition. Only thing water temperature needed for is for the viscosity here. Okay. Okay, that's equation 6130 for the sphere. Okay, so you should be able to use that one without confusion. Okay, so these are all the equations I want to provide you for the cylinder and for the sphere. Okay, so next time we'll look at examples 6.7, 6.8, 6.9. Okay, so I guess that's it for the external flow topic. Okay, if I have time next time, after the examples, I can talk a little bit about the tube bank. Okay, but there's just different equations. Okay, doesn't matter that much. But important part is the single cylinder, single pipe, and the single sphere. Please understand the physics, understand the flow, and please know that the heat transfer is dictated by the flow phenomena in those cases. Okay. Okay, I guess that's it for today. I don't have time for the quiz, but I guess these are the good information for you to have. Any questions? I can entertain maybe one question if you have.
None at the moment, sir. If I get any, I'll shoot you a message.
Yeah, please keep asking me questions. I don't see many of you ask me questions. Use group me. I'm maybe very busy on the Zoom. I have a capstone project. This is the season for them to do the presentation to me. So I'm very busy on the group on the Zoom. But shoot me a message in the group. Okay, group me or even email. I'm more than happy. I'm really like to answer your questions. If you have questions, I answer it. You probably learned it. Okay, so yeah, feel free.
Are you gonna post the homeworks?
Yeah, I can post homework for chapter 6.
Yes, sir.
If you're willing to practice, I will post a set of homework. Okay. Yep. See you. So see you Monday.
Professor, when can I expect this lecture to be posted
I'll post
online?
it every time after class, right? Maybe
Okay.
tonight. Yeah.
All right. Thank
I
you.
think I will post everything. Okay. Yep. I didn't give the quiz today, so I guess you didn't
Okay.
miss.
Because I had a test that
Yeah, I know.
ran
I
till
got your email.
11:30. All right.
Yeah.
All right. Thank you.
You're welcome.